Okay, hello and welcome to some slides on graph theory. So we learned a little bit about this already from the relations slides, but there's plenty more to it. So let's hit the ground running. So I have a fun little motivating example. There was a post on Instagram a few years ago, and I honestly think I've seen it recently again too, talking about a book exchange. All right, and here's the post. Here's the text of the post. And I claim that it is definitely a pyramid scheme. So the idea is like you buy your favorite book, just one of them, and you send it to a stranger. So somebody like the poster knows, and then you're supposed to be able to, just buying one book for one person, somehow you receive 36 books. Okay? So how does that work? And it's totally a pyramid scheme. I can prove it all to you, and we can model it with graph theory. We could model it with directed graphs, which are the things that we drew to model relations. So things with arrows, right? Vertices and arrows, called edges, okay? So the idea of this silly pyramid scheme is, if you read this again, what happens is there's the poster who's posting that thing and you see it. Here's the poster. They have a little node in the graph, or vertex we call it, and then there's you who's reading that post, and maybe you want to participate. The way it works is the poster gives you the contact information, like the mailing address of the person who they learned about the pyramid scheme from. This is the secret. And then you send your one book to them, all right? And then if you want to participate, you tell all of your friends to send their favorite books. It's always 2 people ago, to send their favorite books to the poster, all right? So there's all your friends, and you're telling them to send it to the poster. And then if they want to participate, they tell their friends to send it to you. So like over here, like they're eventually going to send it to you. And like on average, I guess 6 people are naive enough to participate, perhaps. Okay, so that's the idea. And so that's kind of why you send one book somehow. Like the poster sent one book. Like there's a bunch of people coming before this, and somehow like you end up receiving a lot of books. But I can prove to you this is a directed graph, right? It's got vertices, those are the people, and then the arrows are like who's given a book to whom. And this is totally a pyramid scheme, and it won't work out, because eventually the market will become saturated, right? Everybody will have participated. There's going to be one person way down here on the end of the line who like sends their one book to the 2 people ago, and they have no friends who have not already participated in this book's thing. And so all the friends, like there's no arrows coming in, there's no arrows available anymore to come in because they already participated. So there's like a last person, so sad, who can't participate anymore, who's not going to get any books because all of their friends already participated in the pyramid scheme before them. So it's like it pays to start early, I guess. But have you seen that? It's kind of silly, but you can model it with dots and arrows, and that's called a directed graph. And you can kind of see why it's useful and prove stuff about it if you wanted to. We can get mathematical and like legitimately reason about arrows and dots. So that's called a graph. All right, let's talk about graph theory. Let's learn graph theory. So directed graphs, we learned about things with dots and arrows, with an arrow point, right? A pointed arrow. Those were directed graphs. There's like a starting point and an ending point for each edge in that graph, all right? We're going to talk now about undirected graphs. It's a different kind. It's where you have dots and then not arrows. It's like a double arrow. It's like there's a way to get to both. Undirected graphs have no like terminal point. Like there's a way to get, it's like a road network, kind of. So yeah, for undirected graphs, there's no direction, right? You can go either way. Go either way in your graph. And so in that case, to represent this graph, like in code or in math, the way you do it is you make a pair of things. You make a pair of 2 things, V and E, 2 sets, where V is a set of vertices, those are your dots, and E is a set of edges, things that connect your vertices, all right? So let's do it. So like for directed graphs, like we modeled, like for relations, like there was an arrow from here to here in that direction. And so we modeled it like a pair, right? To model just like an undirected edge, like where there's no arrow point, or like you can think of it as having like 2 points. There's no need for any like x coming first before y. You can just model this edge as like, well, if this is x and y again, then like we can model it as like just a set, like x and y are connected along an edge, okay? So none of this anymore in undirected graphs. No more direction. Okay, so yeah, E and V for this graph, what do they look like? So V is the vertices, the things that are involved and connected. Those are A, B, C, D, and E. All right, so that's a set, A, B, C, D, and E. Those are our things in the graph. And then the edges, the things that connect the vertices, we have an edge from A to B, so we can represent that. So it's a set of edges, and each edge is just like there's a way from A and B to get to each other. And so there's no direction. There's no like in that direction or that direction. It's like both at the same time. So each edge is just a set of the two things that are connected by that edge. So there's the AB, okay? And then there's like a BC. And then there's like a BE set, ED, or D, or it doesn't matter, CD, all those things. So you can list it out, okay? I believe that you could do that. But it's just sets of sets now, because like there's no direction. There's no need for A to come before B like we needed for when we were doing directed graphs, okay? There's also a concept of a weighted graph, which makes a lot of sense for undirected graphs especially, because it's like each edge has like a weight or cost to go between something to something else. Like maybe this is like supposed to be like a generalized map, and so like this is like Fresno to Clovis or something, and so like there's like 5 miles in between or something. So like you go along from here to here, it takes you 5 units of cost to get there. So like this is 42 units. Maybe this is like down to one of the, which national park is down there? Like this is to Kings Canyon from Fresno or something. I don't know, 42 miles away. But you get the idea, right? So like there's 8, 12, 5, like there's a weight associated with the graph now. And like you can also have negative edges, be like -17, okay? So there, I made up some example weights for this graph. Negative edges are totally fine. Negative weights are okay. So that's what it means. That's a weighted graph. Maybe like you get free money when you travel in that direction or something. Who knows? But that's graphs in a nutshell. That's an undirected graph. There's a lot of new terminology because we want to study graphs now. There's a lot of words. So one thing that looks a little funny that's usually not commonplace is parallel edges. Like here's vertices A and B. It's possible to have 2 separate vertices to get there. Like maybe this is like a toll road. It's faster. It takes $5 to get there. Or you could take the long route, but that's free. So that's like 0. So something like that. I think that would work. So that's the idea of a parallel edge. Multiple edges between the same pair of vertices. You can also have a self loop. That's okay. Like we had those for like reflexive relations, like coming along yourself. You can have those for undirected graphs too. It just looks a little weirder because it's just like a circle. So that's an edge between a vertex and itself. That makes sense, right? So there's a self loop right there. And these are weird looking things, those and those. And so we call graphs that don't have those weird looking things simple. All right. So simple graphs are graphs that do not have parallel edges or self loops. Okay. So this is totally a non-simple graph. Maybe we should call it a complex graph then. Who knows? All right, more terminology. So for normal looking graphs, for simple graphs, there's some more words that we can associate with them. I guess you can also associate some of these words with non-simple graphs, but usually we care most about simple graphs in this class. So, all right, here's some words. So if we say that if there's an edge between 2 vertices, like there's a way to get there, it's a bridge, then we call those vertices adjacent. So A and B, for example, in this example graph, are adjacent vertices because there is a way to get from A to B. There's an edge there. This edge exists, so therefore A and B, we call them adjacent. And again, the order doesn't matter. It's an undirected graph, so B and A are also adjacent. A and B are adjacent, or B and A adjacent. You can say that, I don't know, B and C are also adjacent because there's this edge right here. They're also adjacent, but where's some vertices that aren't adjacent, like A and D? Those are not adjacent because there isn't an edge like that. So A and D, those are not adjacent vertices. Are not adjacent. Okay. We can also talk about neighbors, which is kind of cute. So a vertex is a neighbor of another vertex if there's an edge between them. So it's like it's a synonym for adjacent. So A and B are neighbors, B and C are neighbors, A and D are not neighbors. Okay. So that's another way to say that. You can also talk about the degree of a vertex. This only applies to simple graphs apparently, but the degree of a vertex in a simple graph is just the number of neighbors it has. So let's see here. Let's think about B, for example. B has how many neighbors? It has 3 edges that connect it to different things. You see that? So that's called a degree 3 vertex. B is a vertex of degree 3. It has three edges coming out of it. See that? And then that means A is a degree 2 vertex. Okay, that makes sense, I hope. And then the total degree, you're talking about the degree of the whole graph at once, that's just the sum of all the individual degrees of each vertex. So the degree of the whole graph, in this example, try to count it while I'm writing all this, whole graph is equal to, well, 2 for A plus 3 for B, 2 plus 3, 3 for C, it's got 3 edges, 3 neighbors, right? 2 plus 3 plus 3, plus 2 for D, 2 neighbors, plus E. E's neighbors, that's 2 of them again, so plus another 2. So that is apparently equal to 6, 7, 8, 9, 10, 11, 12. So the degree of the whole graph is 12. And 1, 2, 3, 4, 5, 6, 7. Sorry, I counted it twice. There's 1, 2, 3, 4, 5, 6 edges, so it's kind of like you doubled it because you double counted each one. So that's an interesting fact as well. Okay, yeah, so if you have a graph, you have an original graph. This is like original graph with vertices for the graph G and edges for the graph G. You can make a graph using that graph. You can make a subgraph. So we say that a graph with its vertices and edges is a subgraph of some original bigger graph if there is a subset relationship like this. Oh gosh, my poor graphics card. If this is a subset of this guy, the subset, it's a subset of vertices and a subset of the edges. Like you pick out the ones you wanted. So the vertices of the subgraph are part of the original graph. It's like a subset, the edges, and you pick out a few of the edges of the original graph as well. Okay, so it's just like it's the same graph. You've just like crossed out some vertices and edges. You pick the ones you want. All right, so let's generate a subgraph here. So if this is our original graph, let's be like, I would like to throw away this edge, and then also this vertex. All right, so that means what else would we like to do? I'd like to also maybe throw away this edge. All right, so that leaves, what does it leave? It leaves this vertex. We still have these 4 vertices. Which edges do we still have? We have this one, and this one, and this one. So that's a subgraph. So like let's draw those all over again. This is a subgraph of the original graph. A, B, C, D, and like this edge we're keeping, this edge we're keeping, and this edge we're keeping. So it's like it's the original graph, but you just threw some stuff out. That's a subgraph. Makes sense, I hope. Subgraph. It involves subsets, which is an easy thing to remember, I guess, hopefully. So that's that. And yeah, like graphs are useful for like I was saying here, like maps. Google Maps, for example, has like a graph of all the road networks of things, and that's how it tells you how to get places quickly. Here's a silly example I saw on Reddit of just like graphs for if there's a way to get from one country to another by roads. It's like here's a bunch of islands just sitting out there, no edges anywhere, but like technically you can get all the way to South America if you take a ferry across Panama maybe. And so like all these things are connected in a sense. Japan all alone, sadly. Canada only has us, and so our degree is 2, right? That's pretty funny. So yeah, those are our graphs. Let's talk about more terms, because why not? There's so much to graph theory, guys. I cannot do it justice. You'll learn a whole lot more about graphs in a four-year college's algorithms class. But here's some more terminology so that we're ready for when we take that class one day. So A regular graph is one where all the vertices have the same degree. So here is a graph where every vertex's degree is 3, and so we call that a 3 regular graph. Like they're all 3, 1, 2, 3, 1, 2, 3. They all have 3 edges coming out of each of them. And so it's really easy to solve for how many, if you know the vertices, how many edges must there be then? It's like 3 times each vertex, over 2 because you double counted it kind of. So that's interesting. That's a regular graph. K, if you use the capital K and you use one subscript, a single subscript, we call that K for complete, I guess. K is called Kn is called the complete graph on n vertices. That is when every possible edge exists. There's n vertices, and every possible edge is there. Some people call it a clique of size n, or an n clique. I know that like informally we pronounce this word like clique, right? Like a clique of people. But in graph theory, you say it clique, like French, I guess. So French pronunciation. So it's a complete graph. Kn is you can call it a complete graph on n vertices, or a clique of size n. All right, that's when you have every possible edge. So this is K6, complete graph on 6 vertices. So there are 6 vertices. There they all are, and every possible edge that could possibly be there is there. Like this guy is connected to every single vertex. And same for everybody else. They all have an edge to get to everybody all at once, right? That's the complete graph. Can't get any more complete, yeah? So then there's also a complete graph, or a K, something with K that looks very odd. So let me make the underlines go away. So if you see K and then 2 subscripts, an N comma M, there's a comma in the subscripts and 2 numbers, that's a weird one. It's like a complete and separated kind of thing. I don't even know if there's a real name for it, but here are the rules to generate this graph. This is what this graph means. If you see K, N comma M, here's what you do. There's N plus M vertices total, and there's like, you put N of them on the left and the M on the right. Like you draw them separately, and like there's like you think of there like being a dividing line between the 3 on the left and 4 on the right. So here's an example of K34. Okay, 3 vertices on the left, 4 vertices on the right, and so they're divided like that. And there are no edges between vertices in the same side. So like there's no edges here or here. There's no way these aren't connected. There's no way to get from either of these to themselves without going to this side, all right? But there is an edge between all of these things and all of these things, all right? So there's a way for each of these nodes to get to everywhere on the right, all right? And vice versa for the stuff on the right. There's always a way. Each of these has a way to get to every thing on the left, each of those 3, all right? So you can also like come up with a formula for how many edges total must there be. But it's like you got a group of 3 on the left, a group of 4 on the right, and K34, and all of these guys can immediately get to these guys, and vice versa. All right, so that's that graph, K34, KNM in general. So with that in mind, let's see. Oh, sorry, I wanted to underline something. So like there's an edge between every vertex in one set, and then every vertex in the other set, but not between sets. Like those aren't there. These aren't here. Okay, so, okay, with that in mind, tell me, how many edges must there be in K34, and is K34 a regular graph? So here is the terminology. We're talking about K34 right now. You tell me. All right, so how many edges are there in K34? Is K34 a regular graph? Well, let's draw it again. Doesn't hurt to draw it. Well, we know which edges are where. Right? This one is connected to all these. This one is connected to all these. Oops. Think about it from anybody's perspective. Just like every single one's got to be in there. Let's see. You've got to be there. You're already connected to those. You still need to be connected to these. You need to be connected to these too. So let's see. Do all of these have 4 coming out on the left and 3 coming out on the right? 4, 4, 4, yeah, 3, 3, 3, 3, perfect. So that's K34. And let's count all of the edges. I don't know why, but I drew the edges in green last time, and maybe that's prettier. Let's just do it again for fun. So this is K3-4. You can go to all those. You can go to all those. Let's just count. That was 3, right? 1, 2, 3, 4, 5, 6. I gotta add 7, 8, 9, 10. It's getting hard to draw. 11, 12. So there are 12 edges. Okay, 12 edges. Do you see why? Okay, this was K3, 4. K3-4, we say. And that is a 3 right there. How many edges? How many edges do we have? We have 12 edges. And do you see how to get that? You got 3 times 4 edges. 3 times 4 edges. That makes a lot of sense, I hope. 12 edges total. Let's see. Equals 12 edges. And is it a regular graph? What does that mean? All the vertices have the same degree. I don't think it is, right? Because all these guys have degree 4 on the left, because they got to go to all 4 of these. And all these on the right, they have degree 3, because they only have to go to 3 things on the left. So if these numbers are different, if it was like 3, 3, then it would be regular, or 4, 4. But right now, because they're different, it's not regular. Okay, I hope you see why. So, all right, so graphs are useful. You can use them to model like road networks and things. And so Google Maps has a graph of all the roads everywhere. How do they put it in a computer? How do we represent graphs inside of a computer? How do we make the type of graphs inside of, let's say, C++? So there are 2 main ways of storing a graph inside of a computer. There are 2 competing things that it depends on your purposes which one you choose. But I think most people, in general, they like to choose the adjacency list representation. So that's when each vertex holds a list of all of its neighbors, like a linked list. So like here's how you define it in C++. Go look up what typedef means if you haven't seen it before, but we can define this type adjacency graph that we can then declare using another type. It's like a synonym for a type. That's what typedef makes. It makes a synonym for a type in C++. So if you say adjacency graph G, it really becomes this. So this is an adjacency list. It is a map of strings to lists of strings, assuming that's how you want to talk about your nodes. So this is an adjacency list. So each, like here's the graph we'd like to represent inside of a computer. You can store it as like each node, its name, this is like a map, mapping to a list of all the things it's connected to. So this is like these arrows right here take like a string name to a list. So that's like it's a mapping. So you can treat it as a map in C++ or an unordered map. That's a hash table. And remember that normal maps are just binary search trees. So all right, so that's how that would work. And so like A, you'd have a entry for key A in the map, and you'd put in the list that comes after it the 2 things that it's connected to, B and C. See that? That's how you represent this idea. And like C, for example, would map to a list of all the things that it can get to, all the edges. That's how you represent the edges. You make a list of all the things that are adjacent. See that? So C is adjacent to A, B, and D. So you'd put that there. So that's how you'd store this graph inside of a computer, like that. So that's one way to do it. That's the adjacency list representation. You can also create a matrix representation of a graph. And so that becomes an n by n matrix where the entries are booleans, 0s or 1s, and they just indicate whether the edge was there or not. So let's see. So this same graph, you'd make a matrix, and matrices just like have indices and things. Like you'd have to give these numbers. Like this is vertex number 1, number 2, number 3. That's how you'd be forced to do it. And so you'd make a matrix, and like this would be the contents of it. Like these are just this is the row number, this is the column number. And you put a 1 if something's there or not. So like, is there an edge? But if there is an edge between 2 and 1, for example, you go here, you find 2, you'd find 1, you put a 1 for true. Yes, there is an edge there. And you'd also do it backwards because it's an undirected graph. So you'd also go like there's an edge between 1 and 2. So you go to row 1, column 2, and also put a 1 there. So you can see like red. Those red ones are caused by this red edge. All right. Similarly for like 2 and 3, there's an edge between 2 and 3. So like 2, 3, put a 1 there for true. And same with 3 and 2. Between 3 and 2, put a 1 there. True, there is an edge there. Anytime there isn't an edge, like between 1 and 4, for example, you just put a 0. So it's false. There is no way to get there. There's no edge there. Right? So that's that idea. And so, yeah, this is a matrix representation. You could model it like this inside of a computer. It's just like a 2D vector. So it's a vector of vectors of bools. That would work. And most people prefer the adjacency list because, like, there's a lot of zeros that you don't put any zeros in the adjacency list. You don't say what's not there. You just say what is there. So this kind of wastes space. This wastes space when there's not a lot of edges. And the technical term for a graph where there's not a lot of edges between everything are called sparse graphs. It's like sparse vegetation in the desert. Not a lot of things growing, so there's not a lot of edges. Not many edges. Okay, so that's the adjacency matrix representation. It's up to you which one you pick. They both have their pros and cons. So yeah, that's how you'd store a graph inside of a computer. Now you try. All right, here's a graph, A, B, C, D, and E, and I would like you to create the adjacency list representation of this graph, call it G, and then the matrix representation of this graph. Okay, so you'll have to like number these, like say that A is number 1, B is number 2. It's like row 1, row 2 in the graph, etc. So like think of this, and you give it a try. All right, so again, you can model this same graph as either an adjacency list inside of a computer or an adjacency matrix. Or just the matrix, I guess. Adjacency list or matrix. So let's do adjacency list first. So it would just be like a map between node names to lists of node names that are adjacent. So like there are 5 things in this. A, B, C, D, and E, and each of those would map to a list of all the things that they're adjacent to. So like what is A adjacent to? It's adjacent to B and C, because these are the edges that get you there. So that's A, it's adjacent to those 2 things, so you make like a little linked list of all that. All right? Or you could model it as like a set type. That's also fine. It doesn't matter. Just you need to know that you can go from A to B. Okay? And then B, it's adjacent to A and C. A and C, I hope you saw that. That's that one. What's C adjacent to? It's adjacent to a lot of stuff. It's adjacent to A, B, D, and E. Good for you, C. Very connected. So, I don't know. Let's just do it in some sort of order, like B, A, E, D. Let's do it in that order. It's just a linked list. The order does not matter. Unless you want to come searching for something, in which case maybe you do want to worry about the order. And then D is adjacent to... What do you got? E and C. It's like C and E right there. There's that adjacency list. And then finally, E is adjacent to C and D. All right, so that's the adjacency list representation of that graph. Let's do the matrix now. So now I have to give like an ordering. So let's just like do it in order. Let's say that the rows and the columns go in order of alphabet order. So like A, this is A row, B row, C, D, E row. This is A column, B column, C, D, E. Okay, so this is a simple graph, so you can definitely put zeros. There's no self loops. There's no way from C to get to C, B to get to B, all those things. It's like those are there. What else? Well, let's just start adding edges. So like there's an edge from A to B. So A row, B column, put a 1 there. Same with, there's also an edge from B to A, right? So it's kind of like, it's always flipped along this line as well. So like from B to A, you also put a 1. So 1 here, 1 here. So each edge induces 2 1s in this matrix. So let's see, we took care of that edge. Let's take care of this one, B to C. So B to C, put a 1. Same with C to B, put a 1 there. Boop. And then, all right, let's do this one, A to C. So A to C, there's a 1. C to A, there's a 1. So I think we took care of these 3 now. Let's do C to E. So C to E, there's a 1, and then same with E to C. E to C, there's also a 1. Let's do E to D now. So E to D, there's a 1, and same with D to E. There's a 1. And then we got C to D as the last one. C to D, 1, and then also D to C. Also 1. And so those are the only places we put 1s. Let me just double check myself. So it's just a 0 everywhere else to indicate that there is no edge between like B and D, for example. There's no, that one's not there. So 0. Not too horrible, right? So this is how you'd store it inside of a computer, and you can look into it now. Like you can go and check, hey, was there an edge? Was there not an edge? So I think you can imagine how you'd use both of these data structures to look into the graph. I'm still not done with the terminology. I'm so sorry. It's just how it works in graph theory. So let's talk about moving around a graph in like more than one way. So like you can imagine like sure there's a way to get from A to B, but there technically like even though there's not an edge from A to D, like there's a way to get from A to D. Like you can go in that direction, use that route, There are terms for that. All right, so let's talk about those terms. So the most generic way to move around a graph is called a walk. All right, a walk from some starting vertex v0 to some ending vertex, let's call it vk. In an undirected graph, it's a sequence of like which vertices did you go through and which edges did you use to get there. All right, you got to be very, very careful because you might have like parallel edges or something. You got to like name which edge you cross as well to get from v1 to v2 because there might be multiple. Okay, so that's like the most generic way. Like that's as much information as you could possibly give. Like there's a way to get from A to C, like to represent this idea, to move from there to there. To start at A, go through B, get to C, using those edges, like this would be your walk. You'd start at A, you'd follow this edge, A to B, and now you're at B, and then you follow this edge from B to C, and now you're at C. Like that's, to represent that, you do it like that. You'd say exactly which edges you got, which vertices you went through, and which edges you followed to get there between those vertices. So okay, it's a little weird, but if your graph is simple, you don't have to specify the edges, right? Because like there's only one way to get from there to there. So technically, in simple graphs, it was like you just be like go from A to then B, then C. Like that tells you everything you need to know because there is just one edge in between those. But in general, a walk is what you need to specify. The length of a walk is you count the edges, all right? So for example, in this walk from here to here, its length is 2 because there was 2 edges that I traversed to get there. Okay, so that's that one. A closed walk is a walk that has been like, walk is the most generic term. Now we're going to start adding side conditions. So a closed walk, it's a walk where the first and last vertices are the same. All right, so it's like you made a little loop. All right, an open walk is where they're different. So technically, this was an open walk. If I close it off, like go from A to B to C back to A, now that's a closed walk if you specify it in this kind of way. Okay, that's a closed walk versus an open walk. And all right, a circuit. All right, a circuit is a special kind of closed walk. All right, we're going to keep adding side conditions. So a circuit is a closed walk, so you start with a closed walk, in which no edge occurs more than once. So, for example, if I go from here to here to here, I can go back around, like make 2 loops, can't I? That's a closed walk. I can still I can move around and get back to myself. I've retraced my steps twice. I've made 2 laps. Okay, that's a closed walk, but it's not a circuit because I reused edges. All right. So this to this to this, that is a closed walk and then also a circuit because no edge has been used more than once. All right. If I start making another lap, now I'm reusing those edges. It's a closed walk, but it's not a circuit at that point. All right, I hope you see that. So that's a new term. No edge. We're talking about don't repeat edges for circuits. So technically, let's see, there's a way to, can I use this graph to show you one where you repeat vertices but not edges? Maybe. Let's be like, we go from, starting from C maybe. You can totally like repeat vertices, like you get back to C twice, like you went in and out of C like 4 times in that thing I just drew. See that? That is a closed walk still. I'm not reusing edges, but I am reusing vertices. That's okay. Okay, I hope you saw that. That's circuits. A path. A path is a kind of walk where you don't reuse vertices or edges. So circuit is where you didn't reuse edges and it was closed, but a path, more general. Usually we care most about paths in computer science. It's a walk where you don't repeat vertices and you also don't repeat edges. All right, so here, let me try you all the options. This is a path from A to C, okay? That's a path right there. But if I start trying to go backwards, go back to B maybe, that is no longer a path because I've reused both a vertex and an edge. I hope you see that. All right, so boop, boop, boop. If I close it off, now I've used A twice. I've used a vertex twice. That's not a path again. All right, it is a circuit though. So there's a bunch of different terms that you got to keep straight. So yeah, paths are when there's no like loops. So there's a path from A to E, taking the long route. Here's a path from A to E, taking the short route. But if I ever try to go back around, like from E to D back to C, now I've doubled up on vertices, not okay. Also, if I like go from A to B back to from B to A, that's not a path anymore because I've doubled up on edges now and vertices. Okay. All right. Final term today: a cycle. A cycle is a circuit. So starting with a circuit, a cycle is a circuit with some more side conditions. It's a circuit of a length at least 1. All right. We know about lengths, right? Go back to the length of the walk. A length at least 1 in which no vertex, except for the first and the last, occurs more than once. All right, the first and last vertices on a cycle, as it implies, are they going to be the same? Okay, so a cycle is a circuit of length at least 1 in which no vertex occurs more than once. So this is a cycle. All right, it's also a closed walk. It's also a circuit. All right, not reusing edges. Let me try to show you a cycle that is not. Or sorry, a circuit that's not a cycle. So this is totally a cycle. All right, the only A is being doubled up on. Not reusing edges, not reusing vertices except for the first one. This one though, from here to here, watch me closely, then to B to C, C to D, D to E, E to C, back to A. This is not a cycle because even though I'm starting at A, ending at A, I'm not reusing edges. I reused a vertex. I reused C. I went through C this way, or I forget exactly how, but I went through C, and oh no, I came back to C. I came back to C. All right, that's not okay if C wasn't the first thing I started at. That's not my starting point. I can't reuse it. So that's an example of something that's not a cycle. All right, so here's a cycle from C back to itself. The second you start going off here again, revisiting yourself in the middle, then it's not okay. Okay? So that's what it means to be a cycle and not a cycle. And I hope just intuitively you kind of see the differences. With practice. Practice makes perfect. You'll get it. Still not done with terminology. We'll never be done. There's just more to learn about graph theory. People study graphs for a very long time. So today's a lot about terminology. Next time will be about algorithms. I still need to finish one. So I will have it finished by the time I record the lecture. So, okay, talking more about terminology. We say that two vertices, I've already used this term, it's a very logical term to use. We say that two vertices are connected if there's a path that you can get from one to the other, all right? So, for example, there is A and D are connected. They're not connected by an edge, but they're connected by, there's a path, like there's a way to get there. You can use that path, or you can use that path. See that? A and F are connected because of that, or because of that. You got options. So that's the idea. So they're connected if there's a path between them, like C and G are connected. Even though there's not an edge, there's a path. All right. You can also, I think you can see also that like every edge here, all of these guys are connected, and there's a way to say that a set of vertices is connected if every pair of them is connected. So it's still connected if there's an edge. That's just like a special case of a path. So like this whole thing, this whole guy right here, all these guys, they're all connected to each other. I hope you see that, right? There's a way pick any two, there's a way to get around, like D and I, boop, there. There's always a path. So these are all connected at once to each other. A, I, H, D, F. That entire set, we call that connected, is connected. You can say that. Save yourself writing thought. So that's that. And let's see, a graph, an entire graph is connected if its entire set of vertices is connected. Otherwise, it's called disconnected. It's like this. This graph is connected. It's a connected graph in total. But this graph right here is disconnected, all right? Because, like, sure, like, these pieces are connected with each other. B is connected to itself, I guess. But this graph is disconnected because you can't, like, there's no way to get from H to B. This graph is disconnected. And I hope you see the parallel between this and like equivalence relations, because connectedness induces a partition of a graph, does it not? So a connected, we call those pieces, like we've partitioned the graph into pieces that are connected, right? Those pieces are called connected components, right? So a connected component is a maximal set of vertices that's connected. So like these guys missing out on the eye, that's not a connected component. It's got to be maximal, as big as you could make it. So this guy, that is a connected component of the graph. This is a connected component. This is a connected component. So there's 3 connected components, and they kind of partition the graph. You can think of it that way, right? That's a lot of terms. All right, let's see if you can get them straight. So here's a graph. It is an undirected graph. I won't tell you terms about it. I want you to discover the terms. Try to do A through E, all right? We're going to talk about paths. Give me the maximum length of a path in the graph. Show me. Maximum length of a cycle. Give me a closed walk. That's not a circuit. Give me an example of a circuit of length 0. Totally fine. Totally possible. In the graph, that's allowable. So back to this. So stare at that for a second. Pause the video. And then give this question a try. All right. So what is the length? What is the maximum length of a path in the graph? So let's do part A. So a path is when you cannot repeat vertices or edges. So if you can't repeat vertices, it looks like there's a way to like visit every single vertex and not repeat any of them or edges. So that's gonna be my longest path. It's one that visits all the vertices. You can't go any further than that, right? So starting at E, for example, there to there to there to there, just going around. See how I'm visiting every possible vertex I can. That's just by definition, that's the longest path I could possibly make, because I can't reuse vertices or edges. That's the longest path. There might be multiple. You gotta, like, this edge is implied. You must use that edge. But like there's a way to go this way. That would also work. Whee, around that way. What's the maximum length of a cycle in this graph? Let's figure this out. So a cycle can't repeat vertices except for the first and last ones. So that means, but we can repeat edges. Let's see. Oh, sorry, it's a circuit. You can't repeat edges because it's a circuit. Never mind. So no vertices repetition nor edge repetition, but it's got to be the longest one possible. So let's see if we can figure that out. So we got to wrap around. Because we cannot repeat vertices or edges, C cannot be included in the longest thing. I hope you see that, because like we'd have to refollow this edge through I. So we reuse the I vertex as well as this edge. So sadly, I think you can see, right, in the longest cycle, this guy can't be included, this edge. So I think the longest one is just going to be wrapping around, right? So let's start at like A, for example. Let's go around between all these guys. Can't go here because we'd be forced to come back. That wouldn't work. But go this way, down here, along this way, back to D, over to A, complete the cycle. And I've not reused edges. The only vertex I reused was the first one. That I'm allowed to do because it's a cycle. That's totally fine. That would be the longest cycle, I would say. I think that's the only option for that one in the graph. All right, let's talk about a closed walk. Let's give an example of a closed walk of length 4 that's not a circuit. All right, so let's think about this. Closed walk is just it's just a walk. Pretty arbitrary. When the first and last vertices are the same, you can totally double up. It's got a circuit though, is when you don't reuse edges. So let's see if we can figure this out. Closed walk that's not a circuit. Here's one. Let's do. Let's go from A to E. If I went back to A like that, that would be totally a circuit. But if I reused edges, which you can in a walk, let's go back from E to B. That's length 4 now. Back to A. Or sorry, that was length 3. So you see that? A to B, 1. B to E, 2, back from B to E, I reuse the edge. That's okay for a circuit, but not, or sorry, that's okay for a closed walk, but not a circuit, and then back from B to A. So here to here, 1, 2, 3, 4, reused edges. That's totally allowed in a closed walk, but not allowed in a circuit. So that's my part C answer right there. I hope you see that. And then finally, let's give an example of a circuit of length 0. Is that possible? Circuit of length 0 is a closed walk in which no edge occurs more than once. So a closed walk is where the first and last vertices are the same. So just like stay here, start here, and don't go anywhere. Well, you came back to where you were. See that? That's technically allowable. You don't follow any vertices, any edges. You just stay at the same vertex. That's totally technically possible to have a length 0 circuit. Just stay there at any of the vertices. Stay there, don't move. That's the idea. Okay, so that's like stay at D, don't go anywhere. That's the answer there. All right, so hopefully you got that. It made a little bit of sense. I have just a couple more things to say. Let's check the time. Doing all right, and then we'll take a break. So let's next talk about Hamiltonian cycles and paths. All right, this is a new fun term. So a Hamiltonian cycle, it's definitely somebody's name, right? In an undirected graph is a cycle that includes every vertex. All right, it's a cycle that includes every vertex, but remember that cycles can't like reuse edges or anything, or in between vertices. So let's see, how do I want to show this to you? Yeah, so a Hamiltonian cycle, it's a cycle that includes every vertex in the graph, but it can't double up on vertices except for the start. Can't also double up on edges. So Hamiltonian cycles in this particular graph, as an example, are, just imagine this in your mind. Here's a Hamiltonian cycle. You can go like boop, 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 got to visit the middle, there, maybe, there, and then there. So that's like visiting every vertex, and I'm doing it in a cycle. So that's a Hamiltonian cycle. There are multiple, right? You can go like this way, down, got to go in the middle somehow, so let's do there, boop. So another shape. Those are both Hamiltonian cycles. They include every vertex in the entire graph. That's pretty cool. So those are Hamiltonian cycles. Let me put those next to each other. Boop. Hamiltonian cycles. A Hamiltonian path is just a path that includes every vertex. So very easy to go from a Hamiltonian cycle to a Hamiltonian path. Just like cross off an edge, right? Just like remove the last vertex in your cycle or something. So here's a Hamiltonian path. Boop, boop, and then boop. Don't close it off because that would create a cycle. Paths can't be cyclic. So this would be a Hamiltonian path example. Okay, there's that one. So that's reusing every vertex in the graph. There's a similar idea for edges, so that's called an Euler circuit. An Euler circuit is an undirected graph, in an undirected graph, it's a circuit that contains every vertex and every edge, which is pretty cool. So what does that mean? Well, it's a circuit. It's not a cycle, so you can reuse vertices, but you can't reuse edges, all right? So it's an undirected graph, and it's a circuit that contains every vertex and every edge somehow. You don't double up on edges, which is really cool. So actually, this example, the reason I chose this particular graph is because in elementary school, I remember that there was a question on the back of a milk carton that was essentially asking you to find, like, draw lines between these dots that don't ever overlap, don't like go over your lines again, that like fill out this picture of like a little house. And technically, it was asking for you to find an Euler circuit of this graph, which is really cute. So that's why I'm reimagining it. So it's going to take me a few tries probably to figure out which one of these, the correct way to do this circuit, but I'll try it. Let's try this way. Boop, 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 boop. Oh, I did it upside down. Oh, man. Okay, so I had it. Let's see. So maybe if I start this way, boop, boop, boop. So there's those edges are covered. Boop, boop, yeah. And that one. That covers every edge. That was an Euler circuit. See if you can recreate that. That is harder than it looks. Okay, so yeah, that's just one that visits. It's a circuit that visits every vertex and every edge. Just naturally, of course, it's going to visit every vertex, hopefully, if it's assuming the graph is connected. So, all right. Yeah, so you're kind of forced to have a connected graph for both of these, right? All right. Yeah, here's a question for you. Find a Hamiltonian cycle in this graph. See if you can do it. Hamiltonian cycle. Well, that's a cycle that includes every vertex. Cycle that includes every vertex in the graph. So let's find it. So like one of these guys. You got a few options, right? Just can't reuse edges. So it's got to visit all these as well as, let's see, as well as all these. So like you can do it in a really weird way if you wanted to. That could work. But like here's one. Let's go from A to B, and then we'll like work on the inner ones. Boop. Or I'll try it out like this. This way would work. So I'm going all these guys, back that way, up this way, over that way. That would be a Hamiltonian cycle. It's visiting every vertex and not visiting every edge though. It's not doubling up on any edges that are disallowed. There's definitely multiple of these. It might be fun to write a program to like try to solve for all of them. It'd be a very hard program to write, but it'd be a fun one. All right, I think I have, depending on time, maybe one or two more slides. We'll see if we can do more. So let's see here. I'd like to next talk about a problem called the traveling salesperson problem. It's a fun one. This is a very computationally difficult problem to solve, but here's the problem. It has to do with graphs, of course. Given, let's say, like a list of cities is like the original example, but you can generalize this to any graph. Given a list of cities and the distances between each pair of cities, like what is the shortest route like that a salesperson would want to take to save on gas, the shortest route that visits every city just once and then returns to the origin city where you started, all right? So you can model this with a weighted graph, can't you? Like, just make a graph of all the cities and all the edges or like the roads network split between them, all the ways to move around between them all. And then you just like, you try every possible path through the graph, every possible cycle that you could make through this graph, okay? And yeah, you can model it with a weighted graph and you just try every permutation of visiting those cities in every order. That's very, very computationally intensive though. Like pretend that you wanted to visit every state capital. All right, there's 50 of those guys, or in at least the 48 states that are connected. Then that would take, like, you'd have to try 48 factorial possibilities, and that's a very large number. Like you can't really solve that very easily, very quickly, naively at least. So this is a ridiculously hard problem. At best, our best examples of algorithms that solve the traveling salesperson problem, TSP for short, they are all exponential time. So they are as bad as they could be. Horrible, horrible running time. And so the only way that it would be better than exponential is if p is equal to np, that fun thing that you can look up on Wikipedia or on YouTube videos. If it so happens that these classes of problems are equivalent, then maybe we can find a polynomial algorithm for it. But sadly, we have to spend a lot of computational effort trying to do it. But here is a traveling salesperson problem for visiting all of the state capitals. This is the shortest route that you could possibly take. And kind of cool looking, right? Going between all the capitals. So if you started at Sacramento, like you'd be forced to like, these are the ways, like don't immediately go to Utah, for example. That would be useless, apparently. That would take you too much time. Don't go straight to Arizona either. It's better to either go to Nevada or Oregon. So there. So isn't that fun? That's a fun little idea. Traveling salesperson problem. And let's see here. Dun dun dun. How are we doing on time? I might as well like move this once and introduce you to the idea that we're going to talk about next. So let's talk about graph traversals. All right. So the goal is to like solve for these things, solve for this, answer this problem using our computer representations of graphs, right? That's where we're going with all this. It makes sense to want to go there, I'm sure. And so like we would like to make Google Maps. How do we figure out the fastest route between cities? Like in many, many applications, you got some graph that represents something that you care about, and like you want to look through the graph. You want to visit every vertex for some definition of visit. You want to go through the graph in total, like you want to move around, see where you can go, or you like want to search. You want to search for a way to get from like one vertex to another to see if they're connected at all. Like these are things that you might want to do. Like for example, you might want to solve a maze. All right, so maybe you're stuck in a maze, and there's a way to model a maze as a graph, and then you can use one of these algorithms that we're trying to talk about here to solve for it. So like if this is your starting point and this is your ending point, you want to see how this is a graph? Watch. Starting point, ending point, make those nodes. And then, just like every spot that you can go to in the graph, make vertices and edges. Like you can move that way. There's a vertex that like kind of represents this kind of spot. This kind of spot. Do you see how these are all vertices and just like edges if you can go there? So there's no edge that way, for example. And there's definitely no edge that way because there's a wall there, but you can go from here to here. Those are connected from here to here. And like you can go out in every direction and you can solve for like what is the way to get through this graph. And so let's go kind of backwards. This is technically a valid, efficient solution. Like you go a little bit forwards and then you go a little bit backwards and see if they meet at all. It's like one of the efficient ways to solve for how to move around in the maze. So like there's only one way to get around here because like you've been forced to turn corners like this. And then like now you have options. You can either go that way or this way, and like these are connected. So this is how you would model your graph. And eventually, like with the algorithms I'm about to teach you, you could solve for how to get, you see how there's a connection there? How to get around and out of the maze. See that? So that's pretty cool. So like you could search. You could do a search between S and E, see if you find a path to get there. You can ask for the smallest path, the shortest path. There's ways to do that. So yeah. You'll never know when a whole lot of problems can be turned into graph problems, and that's why people study them. That's why there's so many ridiculous terms. There's so many terms for graphs because there's so many different problems you can represent with graphs. So yeah, I'm going to teach you a lot of algorithms now, and like ones that visit every vertex, or search for one vertex starting from another, or that do cool things in general with graphs. So I'm going to teach you a bunch of algorithms right now, and there's some more theory to them, at least one of them, at least most of them. I'll show you a fun algorithm all at once at the end of these slides. But yeah, we'll hit the theory a little bit harder. Let me just tell you that now. We'll hit the theory a little bit harder in the trees chapter, because a special case of graphs are trees, and like as you traverse graphs, you create things called trees, which you know about binary trees right now, but there's more generic trees, just like we learned about directed graphs. There's also more generic undirected graphs. So yeah, that's I think where I want to stop for right now. That's good enough on time, and we will continue with some traversals of a graph next, like a search algorithm. The first one will be depth first search. So I will see you. I'll see you then.